So the last thing I'd like to discuss in this lecture is how to use the Nsight Systems tool to look at the system performance around our matrix multiplication. So this is a separate tool than Nsight Compute, and it's more related to how work is delivered effectively to the GPU. So this is understanding not in detail how the GPU kernels perform, but how the system is managing the GPUs and delivering work to them. It's similar to Nsight Compute in that we have two separate interfaces. There's a command line interface that we can use to record data, and a GUI interface that we can use to analyze. And so, like Nsight Compute, we will use Rye to record the data about some programs, and then use the GUI on our own client system to analyze that data. And so if you followed along the original instructions, you already have this installed. If you don't, you can consult the slides, which will show you how to install it on your own system or EWS. So for the rest of this lecture, we're going to talk about two more examples. One is 2.5 and one is 2.6. Both of them are the joint matrix-matrix multiplication, though we're not really going to be focusing on the performance of that. We're just using it as an example. What we're really interested in is the performance of the data transfer and when the data transfer takes place relative to the matrix multiplication kernel. So 2.5 is kind of the traditional way to do things, where we copy the two matrices onto the GPU, then we do the kernel to multiply them, and then we copy back. And in 2.6, we employ a technique to overlap the data transfer for the matrix multiplication with the multiplication itself. Unlike the previous files, we're going to be looking at sort of the end-to-end time from when we start the first copy, then do the kernel, and then complete the copy back to the host. So we're not interested so much in the kernel performance, but in the performance of the entire operation, including the data transfer to the GPU. If you want to run this code yourself, it takes some similar arguments to the previous code, where you can change the number of measured iterations and the number of warm-up iterations. So if you're using Rye, the Rye build file that we provide does all of this for you. If you want to run this code on your own system, you're going to do nsys profile. So nsys has a number of subcommands, so we're going to do the profiling command. And you're going to give it the output name, and it's going to append this qdrep extension to it. So that's the first option there. And then, like the Nsight Compute tool, you tell it the name of the binary that you want to run. So in our case, that's 2-5-pin-joint. And so you can do the same for the 2.6 binary as well. But again, if you're using Rye, you don't need to do this. It's already in your build folder that you downloaded previously. So when you open up Nsight Systems, just like Nsight Compute, you'll need to import the files, which you can do with File Open. You'll see something that looks kind of like this once the files are imported. That main view there is a timeline from left to right. So time starts at the left and proceeds to the right. And each row is a different system performance regime that's being evaluated. So there's all the CPU cores and how busy there are. Every single thread in your application will be in there. Most of them start off hidden because Nsight has correctly figured out that most threads are not very interesting for your program. And then if you mouse over any of those time spans, you'll get additional information, and you can also see events on the bottom of the screen. So you can open all of the files and they'll show up in different tabs and also on the left side. So what we're going to look at first before we look at it in Nsight is this is sort of a graphic of the timeline that's going from left to right. And so I've shown three different kinds of activities here. We'll have one transfer activity that's CPU to GPU. And so first we'll transfer the A and B matrices to the GPU from the CPU. Then we'll launch our kernel, which computes the product matrix C. And then we'll transfer that product matrix back to the CPU. And so our total time is going to be the time that it takes to do the host-to-device transfer. So that includes copying both A and B, plus the time it takes to do the kernel, which can't start until we've finished copying B, and then the time to copy C back to the host for the total wall time of this application. And so this kind of corresponds to this view in Nsight. Most of our application time is not taken up by the actual GPU activity that we're interested in. So when we first load this up, there's a lot of overhead sort of initializing the GPUs and allocating data and generating data. So that's the main time span there. So the other thing that I'd like to point out is there's a lot of CPU activity that we're not really going to drill into in this class, but that information is there if your application does a lot of CPU work. Those NVIDIA tool extensions annotations that I mentioned earlier in the lecture, this is where they can show up. So if you look at the source code, you'll see that we annotate the region where the data is being generated, and so that shows up here. The actual GPU activity is at the bottom of the timeline, and you'll need to expand the view of that activity by clicking some of the arrows on the left pane of the timeline view. And so if you do that, you'll get a row for all the different kinds of GPU activity for all the different GPUs and the streams that that activity is in. And you'll want to click and drag on the timeline in order to zoom in until we can zoom in to a single iteration. And so now you can see that in this particular iteration, this is how it corresponds to that cartoon that we had before. So on the left side, you can see two host-to-device transfers to copy the data to the GPU. You can see our kernel executing there in blue, the MyGem kernel again. And then the device-to-host transfer afterwards to copy the result back to the CPU. And so we can see that actually in practice on the system, just like in our cartoon and in our expectations, these things happen back to back. So we do the first two copies, then we do the kernel, then we copy back. And so the total time is just the sum of all those. And you can see that even though we managed to make the kernel pretty fast, right, this is the joint kernel, now most of our application time is actually controlled by getting data to and from the GPU and not the kernel time itself. Luckily, we can improve this performance if we notice that the matrix multiplication we could actually split up into some number of submatrix multiplications. So here I've represented the A and B matrices each with 2 parts and the product matrix with 4 parts. And so we can compute the product matrix with 4 different multiplications of the subparts of the A and B matrix. So for example, the upper left quadrant of the product matrix can be computed with the top half of A and the left half of B. And so in this manner, we can split up the product matrix into 4 different smaller matrix multiplications. So the idea here is that we can reduce the overall wall time by overlapping some of the computation for C with transferring data from the host. So first, instead of transferring all of A and all of B to the host, or to the GPU, we can transfer A0 and B0 to the GPU and immediately start computing C00 while we start transferring B1 to the GPU. And then once B1 is on the GPU, we can immediately compute C01 while transferring A1 to the GPU. And once A1 is on the GPU, we can finish the rest of the matrix multiplication. The other thing we could potentially do is immediately copy results back to the CPU as soon as these submatrices are done. So as soon as C00 is done, we can start copying it back while we're potentially working on the next matrix multiplication. And so the 2.6 program is implemented in that way. And what this should hopefully look like is we have a much shorter time when we start copying the matrices to the GPU before we can start doing the multiplication. So the total amount of time spent copying the matrices to and from the GPU is the same, but we can overlap that time with our execution. And so the question then becomes, are we actually able to overlap all of these things the way that we think we are? And we can use the Nsight Systems tool to see what that looks like in practice. And so on the top, I've zoomed into our original multiplication where we copy all of the data and then do the multiplication. And these 2 graphics are not to scale, but that top one takes about 3.5 milliseconds. And on the bottom, you can see that we have this overlap now. So we have 4 transfers now instead of 2, because we have 2 pieces of A and 2 pieces of B. But you can see that as soon as we transfer the first piece of A and B, we can start immediately a multiplication while we're simultaneously transferring the next part of A. And so in this way we can overlap the transfers with the computation. And we can do the same on the way back. So now we only see half of the host to device data transfer and 1/4 of the product matrix transfer exposed in our timeline. The rest of it is overlapped with the kernel calls, which improves the overall performance of this multiplication. So now that we've seen how to use Nsight Compute and Nsight Systems, there's a few questions that if you want to explore these tools more, maybe you should investigate the answers to these questions. So there's some programs we didn't talk about, but they're similar to the ones we did that are in the folder. And so one thing you might look at is, if we use different methods to allocate the data, does the bandwidth that we get for transferring the data change? And you can either measure this using events, or you can use the Nsight System tool to see the transfer speed. So that's one thing you could look at. We only talked a little bit about the joint matrix multiplication, but if you're curious, you should try to figure out how we could improve the performance of that kernel. We talked about a few different problems with it. And the final question is, can you improve this overlapping matrix multiplication performance further? Maybe by splitting it into 9 or 16 submatrix multiplications? Or can you develop a performance model to say what the performance will be, depending on how many submatrix multiplications you do? If we use an additional third stream, so we have one stream for host to device, one stream for the computation, and one stream for device to the host, will that improve the performance of the application? Can you even overlap 2 copies in different directions on the system that you're on? So if you're interested in experimenting a bit with these tools, feel free to see if you can use them to answer some of these questions. A lot of the resources in this talk I've pulled from other places. So 2 things I want to call out is the documentation, of course. So if you're ever confused about how to do something, take a look there. I wouldn't recommend just reading through them, but if you have a specific question, that's a good way to get to answer. There's 3 posts on the NVIDIA developer blog related to Nsight Systems and Nsight Compute. They can serve as kind of a nice introduction to those, so I'd recommend checking those out. And particularly for understanding stall reasons, occupancy, and workload analysis, there's a few resources scattered around various NVIDIA websites. And so I've put them here. So if you have questions about what a specific stall reason means, or what a particular part of the CUDA memory model is, I would recommend looking at those. Like, for example, what local memory means, something like that. So there's plenty of other things about CUDA performance profiling that we didn't suggest or didn't discuss. One is their techniques for using CUDA events to measure operations across multiple streams. You can also use the GUIs of these 2 tools to start profiling, so you don't have to use the command line interface. We can't do that with RAI, but if you have access to your own GPUs, you can do that. You can run them locally on the system or connect remotely to systems. So these are things that you could experiment with yourself if you have access. You can also time certain operations in GPU kernels by accessing 2 functions called clock and clock64. You can go ahead and look up how to use those. Those will return the number of clock cycles that elapse between calls, and you can use that to estimate the time of particular operations in the CUDA kernel potentially. And you can also write sort of custom profiling code using the CUDA Performance Tools interface library. This allows you to register interest in particular metrics or record particular metrics on your own. And so that's an option. That's much more complicated, but it's an option for you to look into if you're curious. So I hope this was interesting. Feel free to reach out to me if you have any questions. My email address is my last name @illinois.edu. Thank you.